Okay, so here's where we were last time. We were talking about how to deal with this double integral. Let's see here. So this one here, right? So we were looking to find the volume bounded between these two surfaces, and we've already talked about a lot of the setup. So bounded between, we talked about what that means. We drew a picture showing these two surfaces, and we identified this volume bounded between, right? And we wrote down that we're going to have an integral here of what I'm calling, of course this is a double integral, h of x comma y dA. And the argument we made there, let me just remind you, is that even though now what we're accustomed to, the problem that we have seen before that, as volume relates to a double integral is volume, sitting above a region in the xy plane, that goes all the way down to the xy plane. And this one doesn't, right? So this is geometrically a little bit different, but it has a lot in common in that this height, there's our height, right, is still being multiplied by an area. Okay, so height times area is still morally the same formula. Now, it's a little discomforting that it's not exactly the same geometric example as we saw previously, but it remains that what we're doing is we're taking this solid. We're taking this solid here. We're slicing it up. Now we're slicing it up in two vertical directions. The punchline of which is that we're also slicing up. We're also slicing up our this shadow down here. Let's see if I can do a decent. Yeah, okay, there we go. So we're slicing up that shadow, and said differently, if we slice up this shadow, if we look at these little pieces of area one at a time, and if for each little piece of area we multiply area times this height that I have circled in red, what we're doing is we are exactly adding up the volumes of a bunch of these little, what I called French fries last time. Right? So it's still a Riemann sum. It's not volume under a surface. It's a Riemann sum, which happens to give us the volume between two surfaces. All right. So now a couple more details. So this is about where we left off last time. A couple more details. What is this height? Well, the height is pretty easy to write down. It's going to be this z-coordinate. Oh, wrong color. Let's see. I'll use green is fine. Okay, it's this z-coordinate. Let's see now. Where is that point? That point, you got to look at your picture. This picture says that point is a point on this plane with that equation. So we're going to look at that z-coordinate minus, I'll use purple here, this z-coordinate. Where is that point? That point's on the paraboloid, which has that equation. So the height, our integrand, is going to be the difference of two z-coordinates, right? We're computing a vertical distance. That's the difference between two z-coordinates. So I need to, in the green equation and the purple equation, I need to solve for z and subtract. Specifically green minus purple. Right, and that gives us then for this height, we get 4 minus x squared plus y squared. Everybody happy with that? Okay. So the picture, I'm a big believer in good pictures. Right, it really helps a lot. The picture tells you very often what it is that you need to write down in your algebra. So do yourself a favor, draw yourself a nice picture. Draw yourself a big picture. It's easier to make a good picture if it's reasonably good size so you can see what's going on. Okay, so that gets us down to this right here. And all that remains is to find the bounds on our double integral. Now, what are the bounds on this double integral? Well, we look back at the picture, and there's a lot going on with integrands and stuff. But remember what we decided is that we are, in effect, slicing up this shadow. Right? We started off by slicing up volume, but we realized that in the process of slicing up volume, we're slicing up this shadow of the volume as well. So I just need to look at this shadow and decide, well, what's the range of values of x and y on that shadow? And this is an awkward point of view on that shadow. I'm looking at it kind of from an angle. You know, it's a two-dimensional thing that I'm looking at in a three-dimensional picture. Why am I making my life so hard for myself? Let's not work off of this picture. Let's make an easier picture. By the way, how do I know what the equation for the edge of this domain is? Right? How do I know what this equation is right there? Well, those points come from these points. Those are the points where the z-coordinate from the first surface and the z-coordinate from the second surface are the same, so I need these to equal to each other. So I need these to equal to each other. Right, so this is a circle of radius 2. Everybody see how that comes from the picture? Please don't make the mistake of just taking whatever you see in one equation and setting it equal to whatever you see in another equation. I mean, what if this plane, instead of being z equals 4, what if it had been 3x plus 4y plus 5z equals 6? What if it had been that? I can't tell you how many times I see students that will set just kind of feeling like, isn't this what you're supposed to do? Just set this algebra equal to that algebra. And of course, that's not a thing. Right? The point is, we're looking for x and y coordinates. We're looking for these x and y coordinates. That corresponds to points where a certain thing happens, and namely where the one z is equal to the other z. So don't set that equal to that. Doesn't make any sense. You want to set that equal to that, because those are the two different z coordinates in question. So, heads up, you might have to solve for z. Okay. All right, but of course that's not the problem we're looking at right now. Okay, so here is our circle of radius 2. You can slice this up in either direction. Suit yourself, doesn't really matter. Arbitrarily here, I'm slicing first in the y direction. So we're doing slices like this. Right, you can persuade yourself without too much trouble that there's the first slice, here's the last slice. Now how do I find those values of y? Well, you have to think about what you know about these points. And now this one's kind of a freebie, right? Because, well, those points are the top and bottom of it's a circle of radius 2, so you know they're plus and minus 2. But what you could argue here is that what I know about those points is that those points are on this curve. Well, they're both on that curve, which has that equation. I'm interested in knowing what y is. So I need to solve for y. There's a temptation to write square root of 4 minus x squared, but of course that's not all you know about these points. I also know that those points, just by the symmetries of the picture, those points are on that curve where x is equal to 0. And so that term goes away. So you have plus and minus 2. Everybody happy? Okay. Now again, of course, perfectly obvious in this case, and you can argue that I understand the geometry of circles. You can say plus or minus 2, but in a situation where maybe it's not so obvious, right? Think through what you know geometrically, write it down algebraically, solve the algebra. Okay. So, y goes from negative 2 to 2. Now, we're going to fix a value of y, some value of y, and on that y slice, we then want to know what's the range of values of x. This is the same process we talked about last time. Well, the lower bound corresponds to that point. That point is on this curve. That curve has this equation. Now I want to know the value of x. Solve for x. Square root of 4 minus y squared. And yeah, I know what y is, but it's y, right? It's whatever value of y I happen to be looking at in that slice. So I don't plug in to get rid of it. I leave it there. I'm looking for what this x bound is as a function of y. Yeah? Everybody happy? No, I just made an oops. Anybody want to catch my oops? What did I do wrong here? Yeah. Good. So I just wrote square root as if that's the way you undo squares. Sloppy. Right? So I have to first write, plus or minus, and I'm not sure which one, 4 minus y squared. That's how square roots work. And now we've got to look at the picture and decide, what do I know about this specific bound, not that one, right, but that one. Well, of the two, this is that x1 is clearly negative, and so I take the negative square root. Yeah? Everybody happy? So be careful with that. It's real easy to step on that little landmine and, accidentally forget a minus sign. Very similar reasoning for the other. I'm going to whip through this one super quick because I think y'all are starting to notice the pattern here. For this upper bound, corresponds to that point. That point's on that curve. Curve has that equation. It's the exact same algebra. You solve for x, it's the exact same result. And then just this time, clearly we want the positive square root, not the negative one. Yeah? Everybody good? Okay. And that gives us this result here. There's that height that we talked about. That's our integrand. Here's the bounds that come from the domain. But the thing that makes this problem interesting is that we had to infer our domain. We were not told in the statement of the question what the domain is, right? We were just looking for the volume between two surfaces, and we had to look at this picture and figure out that in order to address this volume, right, we have to view this as an accumulation over that yellow disk domain, just because of how we slice up that volume. Okay, let's do another example. Let's see here. What is now? I got ahead of myself. So how do I know which way to slice? You can slice in either order, but the fact that you can slice in either order doesn't mean it's going to be equally convenient in either order. So how do we make good choices? I'm going to start this conversation by making a bad choice. Show you what that looks like. So here's the problem I want to consider. Here's the same question that we talked about last time. We have two parabolas that are intersecting, and I want to look at this region, bounded between these two parabolas, and that's our domain for some calculation, whatever that is. Okay. By the way, I'm going to do that fairly often, where I'm going to say we're interested in computing some quantity. We're doing a double integral. Let's not worry about what the application is, and therefore let's not worry about what the integrand is. Let's just worry about the domain. If I'm interested in computing a double integral over this domain for whatever reason, there's plenty to talk about in how do we slice up the domain, what are the corresponding bounds. And the application just tells you what the integrand is. We know the integrand is going to be what it's going to be. Okay. So there's our domain, and I would like to address this from this slicing point of view. Let's do our y slicing first. Right, so my dy integral is going to be the outside integral, and so we come up here to ignore this for the moment. We come up and say, okay, slicing perpendicular to the y-axis. There's our slicing. Go through the usual algebra. This lower bound comes from that point, that curve, blah blah blah, y equals 0. The upper bound is going to come from this point, which is on that curve, which blah, 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 algebra process, and we get y equals 2. So there's temptation to start with saying y goes from 0 to 2. Okay, so we write this down here. So y integral 0 to 2. And I'm about to run into a nasty problem that it's hard to see it coming unless you know what to look for. Let's think about this process of as I go from 0 to 2, right, looking at these different y slices. For this slice, how am I going to find my x bounds? Well, this bound comes from that point. That point's on that curve, which has a certain equation. But as I go through this slicing process, if I slice, not down here, if I slice a little higher up, maybe there, right? Then my bound is going to come from that point, which is on that curve. Clean up my picture now. So what we have is that my bounds, my lower bound is defined by points that are sometimes on that orange curve, but sometimes on the blue curve. So what algebra do I use? When I'm trying to find my bound for x1, do I use the orange algebra or the blue algebra? It's a problem, right? Whichever one I pick is going to be wrong for certain values of y. So we have to be concerned about this, and there's really only one way to get around this, having chosen, as we have, that we want to do our y slicing first, and that is to break this y integral up into two different pieces. I have to recognize that for these values of y, between 0 and 1, I have a clear, consistent picture of, look, my slices look like this. This lower bound comes from that point, and that point is consistently on that curve. So y from 0 to 1, I'm looking at this algebra to get my bounds. But for these values of y, and now this is why I have the second picture over here. I need this second picture to consider the second case. For y goes from 1 to 2, my bounds, given a slice, my bound, my lower bound in this case, comes from that point, which is on that curve. Okay, let me do a better job of, which has that algebra. So, as I've got it drawn here, for some values of y, as y is between 0 and 1, the green algebra dictates my bounds. When y is between 1 and 2, on this right picture, the blue algebra dictates my bounds. So I have to break this up into two separate y integrals. I can't just naively say, well, the first slice is when y equals 0 and the last slice is when y equals 2, because the subsequent algebra inside of there changes when y is equal to 1. Okay, so I've got to break it up like this for when y is between 0 and 1. I already forgot what the colors I chose. Let's see, green. Yeah. X bounds are determined by that green algebra, and when y is between 1 and 2, the x bounds are determined by the blue algebra. You get these two separate nested integrals. Yeah? Everybody happy? Questions so far? So let's look now at these this resulting, here's apparently our alternative. The last time we looked at this example, let's see, where was the yeah. No. Hang on. Yeah. Last time we looked at this question, that was the algebra that we ended up with. There was our nested integral. There's only one of them. That's nice. The bounds are polynomials. That's nice, right? I mean, keep in mind, by the way, this inner integral here, whatever happens in this inner integral, those bounds are going to be part of the result. That means that the bounds on the inside integral are going to be part of your integrand for the outside integral. So, we're kind of accustomed from single variable calculus saying, don't worry about the bounds. I mean, it's just whatever. That's what you plug in at the very end. It's ugly though it may be. It's just ugly that you plug into a function and declare victory and it's game over, right? That is not true anymore. Now, whatever's in those bounds, that's going to be part of your integrand. For an integral, you're going to have to take antiderivative. So it is, in fact, quite good news that those bounds are polynomials. Yeah? Okay. So now let's look at where we are here. Two things I really dislike about this this result that we're sitting on. On the one hand, there's two integrals to compute. That's double the work right there. Right? But even worse, my inside bounds have square roots in them. That means that my outside integral is going to have square roots in it. I'm going to be doing an integral whose integrand involves square roots. This is look, we could probably do it, right? But it's going to be relatively inconvenient. Okay, so highly undesirable result. Okay, so I just want to point out two ways that you can anticipate this kind of thing. I mean, obviously, one thing I suppose you could do is you could just write this down, go through the process, draw the picture, think about the bounds, and it's a certain amount of trouble to write down exactly what this would end up being, and then write it down the other way and compare and contrast, decide which one you want to do before you actually do it. And I'm not saying you shouldn't, but that does sound like more work, right? So here's a couple of ways that you can see this coming in advance. One, why did we get two integrals here? Ultimately, where was the tip-off that we got two integrals here? The tip-off, let's just go back to the picture. Tip-off is that the bounds for my x integral jumped, right? When I was down here, I got one answer versus when I was up here I got a different answer. Now how did these x bounds change from one formula to another formula? Well, it changed because this point jumped from the blue curve to the green curve. And rhetorically, how did this purple point jump from the blue curve to the green curve? It jumped because these two curves intersected. And the way I like to say that is these two curves, there's a corner in my domain, and in my slicing process, in my y slicing process, I slice through a corner. So that's a geometric tip-off. I think that's just, pulled back as far as you sort of as superficially as you can make it. The moral here is try not to slice through a corner in your slicing process. If you slice through a corner, corners come from curves intersecting. Curves intersecting means that this point could jump from one curve to another curve, which could mean that this bound is going to be different formulas for different values. So try not to slice through corners is the first moral. Second moral, let's look back down at this answer. Another thing that we didn't like about this was there's square roots in there, right? We don't like square roots. Well, where did those square roots come from? Those square roots came from the fact that I ended up having to solve for x in this equation. Right? So when you have algebra that's part of the definition of your domain, look at that algebra and just ask yourself in advance, which variable would I rather solve for? Right? So now you look at here we have y equals 2 minus x squared. Solving for y sounds great. It's been done, it's easy to do, and I get a polynomial which I like. Right? So solving for y sounds good. Solving for x, I'm going to have to do the algebra, and the result involves square roots. So solving for x seems highly undesirable. Whichever variable, if you just think it through, if I don't want to solve for x, don't make it something I'm going to need to solve for. Don't make it the inside differential. Right? So there's different ways to say that. Always slice first with respect to which variable, one variable or the other variable. I think the easier way to remember it is identify which variable you don't want to solve for. Don't put that one on the inside, thus creating a situation where you do have to solve for it. Yeah? Everybody see the motivation there? So now these go ahead.
So would you have to slice?
Yeah, I would suggest slicing the way we did the first time. So the first time we did this problem, we did like this. Right? And notice we're never really slicing through corners. Now you could say, well, you started at a corner. Sure, but I was already going to start a new integral there anyway. I'm just getting started, so it's no problem to say, oh, you have to start a new integral. I was already doing that. And I ended at a corner. But again, no problem. I was done anyway. Right? So, yeah, so that's what I would do. Yeah. Let's see here. What was I going to say? Yeah. Well, anyway, so keep this in mind when you're looking at your domain, and you're looking at a given problem and trying to decide which order to slice it up. Now, let me caution you against one thing. Some students decide, I always get confused slicing that other way, so I'm just, I'm just going to always do it this one way. He said we could do either one we want. I want to always do dx on the inside, or I always want to do dy on the inside. If you make that choice, you're very likely, half the time, you're going to be forcing yourself to do something that's much harder. Furthermore, if you do end up choosing to do one that's much harder, it pretty much exposes that you don't know how to do it the other way, right? Which is not a good thing. So you really kind of have to make good choices on this kind of thing. So there's a couple of examples. Let's look at this one here, just kind of cosmetically. Which way do we want to slice? If we slice first perpendicular to the x-axis, you notice that we slice in the middle of our slicing process. We slice through two corners, and so we're going to have 1, 2, 3 separate integrals. Right? On the other hand, if we slice first perpendicular to the y-axis, I guess you could say you still kind of slice through two corners, but you're slicing through them with a single slice, and so you only have 2 separate integrals instead of 3. So I would do it that way. I think that's the clearly better way to do it. Okay. Now, what about the worry of, oh yeah, which variables do I want to solve for in terms of which others? Well, that is a line. I'm just as happy to solve for y in terms of x as I am to solve for x in terms of y. It's going to be, something times variable plus something. Either way. Doesn't matter. Likewise, all the rest of these edges, they're all lines. So, it really doesn't matter in that case. Okay. Here's one. This is weird. So, I think there's a strong case for slicing this way. And let's just think of it in terms of, I am going to slice through a corner there. But think about what would happen if we sliced like this. Life is good for a little while. You have straight lines giving you your bounds. That's all good and everything. But then as I slice through up here, horrifying things happen. Right? Where not only am I going to have to solve, let's see here, I'm going to have to solve for, on these points, I'm going to need to know what are these x bounds, and I'm going to have to solve for x, and that means I'm going to get arc cosines, right? It's even worse than that. This one is arc cosine. This one is not arc cosine. It's not, arc cosine is always, comes from this part of the cosine function. Right? So you'd have to, think back to your trig, trig symmetries and rules, etc., and figure out what in the world are these over here. Now it's just the negative of arc cosine, right? But then, even worse than that, what about these pieces over here? You're going to have a whole separate thing there, and a whole separate thing there. A grand total, you're going to have 4 separate integrals if you do it. If you do your dy slicing on the outside. And the nightmare of, I'm over-exaggerating, but what are these values? Well, you can think it through, just think through the trig, right? And what are these over here? And it's just, oh my gosh, your bounds on your inside integral are going to be chock full of arc cosine plus this, and such minus arc cosine. That means that your outside integral is going to have arc cosines everywhere. This is going to be a nightmare of an integral if you slice that way. Nightmare. Right? So, I'll go ahead and slice through that corner. I'll accept the consequences. I have to do 2 separate integrals. My integrand's going to involve cosine. Not that bad, right? It's doable. Calc 2. This looks pretty reasonable. Everybody happy? Okay. All right. Okay, so moving along. We're going to go to triple integrals now. I like to segue into the triple integrals question with, this is some stuff that's not in the text of the book, so if y'all want to scratch this down, you can. Or don't forget, by the way, this is all being recorded. Let me just double check, make sure I didn't forget to hit the record button. Yeah, we're recording here. So another thing you can do if you'd like to have, this extra text that I've written down here, you can just wait till you get to the video recording and then just screenshot some stills from the recording. So anyway, suit yourself. So let's talk about single variable integrals. Rewind to Calc 1. And let's see here. There's different points of view on single variable integrals. The one that gets pushed so hard is this one. Single variable integral gets the area under a graph. Which, it has its uses here and there. And is really nice to give you what you might call a fuller picture, to geometrically see all of the participants involved in that integral. So it has its purpose. Sure. Okay. Then you know that there's this other application over here that you can compute, among many other things. You can compute the mass of a one-dimensional rod. Okay. Now, I would point out that different kinds of accumulations are actually more common applications than, finding the area under a curve. Right? It's very rare that you actually need to compute the area under a curve, as it turns out. They use area under a curve as a way to visualize other applications, but usually it's not, the area under a curve is not your actual sort of first, motivation for most integrals that you're going to write down. All right, so fine, 2 different points of view on single variable integrals. Now let's go and talk about double integrals. let's see, maybe I'll zoom out one notch. Let's see here. There we go. Double integrals. Different points of view on how to compute how to visualize double integrals. On the one hand, you can view it as representing volume under a surface, right? And that's fine. And then, we saw as another application, you can compute the mass, let's say, of a two-dimensional region. And again, there's certain temptations. We like this point of view. It's appealing because you can see all the participants, right? In the same way that this integrand gives you height that you can see in the picture, this integrand gives you height that you can see in that picture. And it's just visually very sort of exposed and complete and forthcoming. I don't know what you want to call it. Okay, where, not so much over here. I can't see the density. I have to use my sort of physical, intuition to persuade myself that I have some sense of what's going on there. You can't visually see it. Okay. Likewise for the double integral. All right. So again, a lot of students decide, well, I like the graph point of view, and this is, apparently a necessary evil, and it's going to come up a lot in the applications, but it's not the way I want to think about integrals. Okay, so I want to try to persuade y'all away from that point of view. I think you should think of this as your primary point of view on how to think about integrals. Yet another example of my anti-graph, sentiments. Okay. So what's my argument? Why would I be so against the graph point of view that seems better? And the answer is that we're not going to stop with one-dimensional domains or two-dimensional domains. We're going to have to go on to three-dimensional domains. In other words, said differently, it's not just that we're going to have intervals that we want to chop up and do accumulation arguments on. And it's not just that we want to have two-dimensional regions that we want to chop up and make accumulation arguments on. We're going to have, and it's really easy to motivate, we'll do it momentarily, three-dimensional solid regions that we're going to want to slice and dice, right, into little pieces and make accumulation arguments on solid three-dimensional regions. So what we're going to call a triple integral, and I'll write down the definition momentarily, but let's just sort of argue by analogy here. What would we expect a triple integral to look like in these contexts? And in the graph context, we get a great big question mark. Because if we're viewing single integrals with a two-dimensional picture, right? One-dimensional integral, two-dimensional picture. If we're viewing double integrals with a three-dimensional picture, stands to reason that a triple integral you would expect to require a four-dimensional picture. And I can't even fake it. I can't even pretend that I can draw that kind of a picture or visualize that kind of a picture. Right? So this is a problem. It's a very serious problem. On the other hand, this mass point of view, no problem. You want a one-dimensional integral? Here's a way to visualize it involving a one-dimensional physical application. Two-dimensional integral? Two-dimensional physical application. No problem. Three-dimensional integral. Three-dimensional physical application. And in fact, you could argue that this three-dimensional physical application is more familiar than the one- and two-dimensional. I mean, you think about it. When you say density, what's the first thing that comes to mind? What did they teach you in ninth grade physical science class or whatever they call it? And that's what they call it when I was in school. But they always taught me that density was mass per unit volume. Right? We talk about the density of a three-dimensional solid thing. You kind of have to use your imagination and sort of stretch your open-mindedness to think about the word density, to think about mass per unit area. That's a kind of a let's be open-minded here kind of situation. Mass per unit length. Again, it's not the usual way we think about it. Mass per unit volume is perfectly familiar. Right? So, really natural way to think about an accumulation over a three-dimensional region. All right, so this is a big deal. The reason I like to make a big deal out of it is, for one thing, I want to give students a good way to think about triple integrals that we're about to write down. But I also want to help you avoid stepping on a very common landmine that students step on, which is to think, okay, I've already decided this is how I'm thinking about single variable integrals, and this is how I'm thinking about double integrals, and fine, I'll think about triple integrals that way, right? And then students get super confused because students are thinking, well, double integrals are about volumes and triple integrals are about volumes also. What's the difference? Right? So I emphasize, I'm not saying that you can't think about double integrals this way, and I'm not saying you can't think about single variable integrals that way. I'm saying just be very cognizant, be very conscious as you think about, single variable integrals and double integrals. As you think about them in this way, realize that it's kind of anyway. It's a crutch. It's a peculiar crutch, right? That only has certain benefits, and it's a little misleading, right? I think the best way to think about integrals, and so try to encourage yourself in this direction. The best way to think about integrals is just realize that, forget about volumes and areas and stuff like that. What integrals really are, of course, is Riemann sums. What Riemann sums really are is accumulations. Try to think about integrals in terms of accumulations of stuff. So we're thinking of mass as something that accumulates over that rod, or it accumulates over this two-dimensional region, or it accumulates over this solid. There's an accumulation of stuff, and the total is equal to the sum of the parts, and Riemann sums. And you don't need graphs. All right, is everybody on board? So, again, I'm not saying don't think about this. I'm just saying don't let what I have circled in red confuse you in thinking about integrals in the green sort of way. Okay. All right. So moving along now, let's talk about triple integrals. And here's what we're going to do. Let's suppose we have some quantity that accumulates over this solid. And it's a solid. Now it's not an interval, one-dimensional, Calc 1. It's not a two-dimensional area, double integrals from earlier in this chapter. Now it's a three-dimensional solid region. And I want to talk about some quantity that I'm interested in computing. Mass is a great example. Because mass is, in three dimensions, we're constantly surrounded by mass. We're constantly thinking about mass. We bump into it, stub our toe on it, have to pick it up, right? We have this visceral connection to mass. So that's my favorite example for something that would accumulate over a three-dimensional region. So if I want to compute the mass of this whole thing, and maybe density is widely varied. Maybe the density is, not so much over here, but there's more density over here, and maybe much more density over there, and in a way that depends on not just X and Y, but also Z. Well, however mass might vary, the total mass is the sum of the little masses that there are on the inside. Slice it, dice it up into little pieces, right? The sum of those little masses gives you the total mass, and on each little piece, I can argue pretty easily that, on that piece, what I'm going to call delta M, the amount of mass in that little piece is going to be, whatever the density is, times the volume of that piece. And so, how much volume is there in that piece? Well, it's a box. Volumes is length times width times height. We've already talked about slicing up the x-axis, slicing up the y-axis. Now we just have to slice up the z-axis too. So delta x, delta y, delta z. Yeah, everybody happy? No graphs. Right? This is not a graph of anything. So we can write down that summation. If I want to compute the total mass, I'm going to be adding up. Now, of course, I'm going to be taking a limit eventually. When I do a finite slicing, density is not exactly a constant over each little box, and there's going to be little variations. And so the approximations that I get by multiplying density times volume will have, error, a little bit of error in them. So in the limit, we hope, And it turns out to be the case as long as the function's continuous. In the limit, we hope that these round-off errors go away. So for each little piece, what we're adding up is density times volume. So some function representing density in this case times volume that we've already argued is delta x, delta y, delta z. All right. So this expression will compute our mass for us. Now, I'm going to give this a name and a notation. We're going to call it a triple integral. The notation is pretty easy to motivate. 3 little integral symbols instead of 2 because we're doing a 3-dimensional domain instead of a 2-dimensional domain. So I think it's pretty reasonable choice. dV to represent the delta V. All right, everybody happy? Okay. So this expression, even though I motivated this expression for a specific application of how much mass is there inside of this, this 3-dimensional solid box, it's a general expression that has applications in lots of circumstances, and we're going to call it a triple integral, like so. So this is just a shorthand notation that is going to be kind of a convenience, recognizing all the different situations when we're going to have to do an accumulation Riemann sum argument. Okay, all right. Let me take a pause for a second here. See if anyone has any questions. Feel free. Everybody on board so far? Everybody's good? All right. So let me say a couple of words about the integrand here. So 3 dimensions are hard to visualize, right? I mean, it's all we can do. It's at the absolute upper limit of our ability to visualize geometrically. It's hard to, depending on what your application is, trying to figure out, what your integrand is can be a little bit confusing. What it's always going to be, though, is that we've got some, whoops, what did I just do? Oh, I think my back hit this button here. Sorry about that. There we go. There's always going to be some quantity that we're computing. That quantity is accumulating over the interior. And on each little piece, it's going to be that the quantity in question is equal to something times the volume. Now, what I want to do is open your mind to what we're going to call that, right? It's an integrand, sure, but there's some quantity, and it's something times volume. So that something is quantity per unit volume, and there's a pretty natural word that's highly suggestive of this idea of stuff per unit volume, right? And that's density. So most of the things that you're going to see, most of the integrands for triple integrals, what they're going to be is, it's the thing that you multiply by volume. So what it's going to be is a density most of the time, some sort of density. But you have to open your mind about what the word density means. So again, we're accustomed, 9th grade physical science class for me, something similar for y'all, to thinking of density as mass per unit volume. But be open to the idea it might be something else, right? There's some other quantity that you're interested in computing. Population comes to mind. Maybe you have one of these glass enclosed boxes, aquarium kind of things, but it's not, water in there. Maybe it's some sort of flying insect, little fruit flies or whatever that are flying around in there, and maybe they're accumulating next to the fruit down in the one corner, and so there's greater density of fruit flies over here, and there's less density of fruit flies over there, right? But you could talk about population density of fruit flies, and again, density is a reasonable thing to talk about. It's quantity, in this case, not mass, but number of flies per unit volume. That make sense to everybody? So anyway, heads up, that's going to be the main way that you're going to be thinking about integrands for triple integrals. Okay. So this is exactly that example. Okay, here I have bacteria, but whatever. Total population is the sum of the populations in each little box. We're going to add up over the entire box. That means we're adding up in both the x, y, and z directions. On each little sub-box, population is population density times volume, and thus triple integral. And again, notice the shorthand notation. This little shorthand intermediate step in the development of that Riemann sum is fine. Very common to write things that way. I'm a fan. I do it myself. I like it. Just make sure to remind yourself that there is no p-axis, right? That's not what this is saying. And just make sure to remember, as you know, when you see this, that's what you're really saying. You're saying an accumulation of little pieces of whatever that quantity is. Okay. All right. So now, how do we compute triple integrals? Right. So we've seen some applications where triple integrals answer the question. How do you compute them? This is going to be a hard argument for me to make persuasively. I'm just going to assert that you can compute triple integrals with triple nested integrals. I'm not going to give you a justification for this other than it's just like what happened with double integrals. The reason why I can't give you this argument is because last time the case that we made was to say, oh, well, we already know that this computes something in relation to graphs, but it was volume, but now it would be a four-dimensional volume, and I would have to then make a slicing argument to compute a four-dimensional volume, and this is not something that I can persuade you with, right? This would be an exercise in confusion. So the argument just kind of crashes and burns to be able to make this sort of persuasion. There is also an algebraic argument that can be made. It's really much better to make an algebraic argument. It's bulletproof. Doesn't require geometric intuition. You can trust it more. But the algebra in proving this is sticky, and I don't want to get into that either. This is not Math 212 appropriate. So I'm just going to make the assertion that triple integrals are computed with triple nested integrals, and I hope this is pretty believable. I think it is. Okay. Notice that there's more than one way to order your differentials. In fact, there's 6. Now, if you only have 2 differentials, there's only 2 ways to order them. But if there's 3 differentials, just think about the number of different ways that you can contort things around, and there's 6 of them, as it turns out. So you've got a lot of options, and you can call that good news or bad news. Again, the good news, you have a lot of choices. Bad news is you have to make a choice between a lot of options. So anyway, something to keep in mind. A quick example. This is just to see how the algebraic mechanics work. The algebraic mechanics are it's exactly analogous to the double integral thing. So let's suppose that this is your density, and you are computing mass as a triple integral of density. And we've already made the case for why that would be. And so you get down to this triple nested integral, and we start the integration process. Just don't forget, you have to go sort of inside out. I can't start with my dz integral because I don't know what my integrand for that integral is yet. I've got to evaluate that integrand before I can do that integral. Right, so you have to start on the inside. So we'll start with our dx integral. Don't forget that for your dx integral, x is a variable, y and z are constants. Right, the variables further to the outside are constants. So the antiderivative of 2x is x squared. The antiderivative of 2y is not y squared. Don't make that mistake. The antiderivative of 2z is not z squared because y and z are not variables. Y and z are constants as far as this inside integral is concerned. Yeah? Just like with double integrals. Okay. The rest is algebra. What if you have a non-rectangular domain? This is where things start to get geometrically challenging. If you have non-rectangular domains, I'm going to make the same case that I did for double integrals. Only the domain is needed to determine the bounds, right? That was the case with double integrals, and I claim it's the case for triple integrals. And I'm just going to show you by example. It's a lot easier to just kind of hit the ground running. Let's do some examples, see how this works, see what it looks like, and I think you'll notice that it's morally equivalent to what we did with double integrals, just 50% more because there's 3 of them instead of 2. Okay, so here's our first example. Let's suppose that our non-rectangular domain is this tetrahedron. Right? So this tetrahedron has these vertices at 1s on the various axes, and then it has its 4th vertex at the origin. Right? Nice, easy starting point. Certain easy things to write down about this. It's not hard to persuade yourself that the equation of this plane is x plus y plus z equals 1. Yeah, easy to do. Okay, so how do we slice this up? What are the bounds on the resulting integrals when we slice this up? So I'm going to make a fairly arbitrary choice here. I'm going to start by choosing to do my differentials in this order. Why that order, you ask? In this case, no good reason. Pretty arbitrary. There's nothing in the equations for any of these planes or lines or whatever that seems to favor one variable over another, right? I mean, in that plane, x plus y plus z equals 1, yeah, I can solve for any of them. I don't really care, right? So it's an arbitrary choice, just to get the ground running. I would encourage you, by the way, after we're done with this example, be a really good little exercise, is to do it with a different ordering. Make your own slicing argument, right? Ordering it, pick any one of the 5 remaining slicing choices. Slice it up yourself. Okay, all right. So, starting with our z slices, what are the bounds on our z integral? Come up here. Here's what slices look like when you slice perpendicular to the z-axis, right? Not hard to argue that your first slice is down here, where z is clearly 0. Right? Your last slice, as these slices get higher and higher up here, or the last slice is going to be right there. And now I say here that z is equal to 1 there. How do I know that z is equal to 1? Different arguments you can make. Let me show you the analogy to the argument we've already made. I want to know the value for z here. What do I know about this point? That point is on 3 different planes. That point is on that plane. It's on that plane. And it's on that plane. Does everybody see these 3 planes that that point is on, right? Our upper bound for z is defined by a point. That point's on these 3 surfaces. Got to identify those 3 surfaces. And now I can write down the algebra for these 3 surfaces. This green surface here has an easy equation, y is equal to 0. The purple plane has an easy equation, x equals 0. And this orange plane has an easy equation. We already wrote it down, x plus y plus z is equal to 1. Now, again, I'm interested in this point here. Why am I interested in that point? Because it tells me my upper bound for z. So I'm interested in solving for z in this equation. So there's your algebra. Solve for z. Don't forget that we already know x and y from the green and the purple equation. That's a lucky break. And you can see we get z equals 1. Right, because you can take this, plug in there and there. Everybody see how the algebra works out? Notice this sticks to our process. It's just like the process for double integrals. Bounds are determined by points. Points are on certain geometric objects. Geometric objects have certain equations. It's always that, I want to encourage y'all to always go through that process. Identify the point, identify the geometric objects, write down the equations, and then solve for what you're interested in. Okay. All right, so, 0 to 1. Whoops. Z, 0 to 1. Okay, now, moving along. Can I make a suggestion? This is a bit of a side point here, but so I've talked about the importance of having a good picture. This is a decent picture. Maybe it's not the best picture, but there is something about this picture that I can see that I already don't like. Some of y'all have come to me and talked to me about drawing, and I've made the following observation, but I want everyone to hear this, and that is when you're drawing something three-dimensionally, if the things that you're drawing are actually in space parallel, then when you draw them, they need to look parallel. So I did a good job with this, and for a couple of these cases. So in 3 dimensions, looking at this slice here, that is supposed to be parallel to that, and I drew them as being parallel, so good for me, right? Likewise, this is supposed to be parallel to that, and did a pretty decent job of drawing those as being parallel, but I kind of blew it for the other one. Right, that line is supposed to be parallel to that line, and I don't think I did a very good job on that. So if I were going to critique this picture, I mean, I think it's good enough for these purposes, but that's what I should have done better, though. Is I should have figured out how is it that line ended up being so not parallel to this other one and fixed it. Right. Also, notice I freehanded this. I didn't use a straight edge. Reminder: y'all are perfectly welcome to bring in straight edges for drawing purposes. For the homework, also on the exams, totally fine. So anyway, that could have helped. Okay, so next question. We're going to fix a value of z. We're going to say z is some fixed value between 0 and 1. We're going to look on that z slice. Does that sound familiar? Right? It's just what we did in double integrals. Now we're going to look for a given value of z. We're going to look for the range of values of x. We're going to try to find those x bounds. So here we go. Here's a fixed value of z. We're looking on this z slice. On that z-slice, I want to know what happens when I slice perpendicular to the x-axis. Here's my x-axis. Slices perpendicular to the x-axis are, like that. And I appeal to your geometric intuition. When you take a horizontal triangle and you make vertical slices of it, gotta think through the geometry. What you actually get are little line segment slices like that. Those didn't show up very well, did they? Let's do this in a pencil. You get little slices that look like that. Everybody see that? I mean, you really got to think three-dimensionally about this. I mean, you just have to, let the picture help you. Any questions about that? Let me hit a pause on this for a moment. Okay. All right, so again, we need to figure out what the range of values are. Where's my first value of x? Where's my last value of x? So you look at, keep in mind, we're on this triangular slice. The first slice is going to be there. And it's pretty easy to persuade yourself that slice is going to be where x is equal to 0. If you wanted to write that down algebraically, you could write down you could pick, for example, this point. Right, that point is one of the points on this slice. That point is on several planes, one of which is the plane x equals 0. Right, that point is on that plane, is that equation. When you solve for x, if you know x is 0, it's easy to solve. Okay, so looking at the slices again, where's the last slice? The last slice is going to correspond to that point, right? So the x2 that I'm looking for corresponds to that point. Now let's start thinking about what we know about that point. I know several things about that point. It's on that plane. Thank you, picture. I needed the picture to help me draw that conclusion. Right? It is also on... Let's see here. Well, it's on this plane. And there is a third plane that it's on. It's on that plane. It's on the plane representing the particular z slice that I'm looking at. So there's three things I get to write down. Then let's write them all down. Whoops, wrong color. This blue plane. I know that, let's see, that's the plane y equals 0. Let's see, the yellow plane, we have, what's that, x plus y plus z equals 1. And this third plane, that plane there, well, that's just the plane that describes that there's this fixed value of z that I'm looking at. So, I mean, look, the way I write this down is just to say z equals z, and I feel stupid writing that, but it just, this is my way of communicating z is what it is. Right? I mean, it's a constant fixed value that I'm allowed to work with. So this is just kind of a visual reminder of that. So solve for what we're interested in. Again, we're interested in knowing about this point. We want x for that point. So in this algebra, solve for x. And what we end up with then is, well, let's see here. Y is 0, so that goes away. You solve for x. The y is gone, but there's still that z there. X is 1 minus z. Yeah? Everybody good? Questions? Everybody see the process? Everybody see how I mean, there's this geometric point of view on the process that gives rise to algebra that gives you the answer. Okay. All right. So here you go. Right, our x bounds 0 to 1 minus z. Yeah. Yep. So the x bound, the starting value of x we got by just observing it was 0, and so yeah, this is right. Yeah.
Would those bounds remain the same regardless of what order you took your slices?
No, they absolutely change. Yeah, for sure. So this, just like with double integrals, right? If you're doing a double integral over a rectangle, yeah, it's just like this, and it's easy, and you can just kind of move them around. But if it's not a rectangle, then the inside bounds are always functions of the outside variable. The outside bounds are always constants. Right? So there's no way, this is not possible. There's no way that could work unless it's a rectangle. Right. Okay. All right. So let's move it along. Let's see here. So now we're going to fix a value of x. So we've already agreed that we fixed a value of z. We're looking at a particular z slice. Then we sliced up that z slice with different values of x. Now we're going to fix a value of x. So we're going to look at an x slice of our z slice. Now we've already talked about what those look like, right? An x slice of our z slice. Let's see here. So here's I forgot what color I used. There's our z slice. And we've talked about how an x slice of the z slice looks like that. So now we're going to focus our attention on just that green line segment. And as we do our y slicing, coming down to here, we're interested in now the range of values of y. Want to know what these bounds are? We're going to look on this x slice of this z slice and try to figure out, okay, where it is, so this point here represents my starting value of y, and this point here represents my ending value of y. That make sense to everybody? So here we go. Got to try to figure out what are these values of y. So again, it's all about looking at certain points. My lower bound for y corresponds to that point. That point's on certain geometric objects, one of which is the plane y equals 0. So of course the starting value of y is clearly 0. That's every so often you get lucky and drops in your lap, so that's nice. But for the upper bound, that bound corresponds to that point. Now I got to enumerate again, what do I know about that point geometrically? Well, a few things. On the one hand, I know that I'm on this plane. Let's see, what other planes is this point on? What else do I know about this point? Well, it looks like that's the only plane that it's on. But don't forget, we already know the previous two variables. So we're on the plane that I've described as z equals z. I've already fixed and chosen what z is. So I'm just going to write down z equals z, and I've already fixed and chosen what x is. So on that x slice of the z slice, I know what x is. So I'm going to write that. So again, in here, I want to try to find the y coordinate of that point. So I need to solve for y, and y is 1 minus x minus z. Everybody happy? Any questions? Okay, and let's see here. That's, yeah, there we go. So the range of values of y, the y bounds 0 to 1 minus x minus z. That's the process. It's morally equivalent to the process that we did for double integrals. It's geometrically a little different, of course, appropriate to the context. Okay, so now again, very quickly, let's talk about what are you going to do with this integral in terms of evaluating it. Well, if you're computing a given mass, there it is. Let's suppose density is a given function 6x. How does this algebra crank out? Well, just don't forget to think about what's a function of what, and then also don't forget that when you plug in, right, well, let's see here, I'll highlight like this. That which was a bound is going to plug in and become part of your new integrand. Just like with double integrals. Okay. All right. So just a quick reminder of how this process works. I mean, again, you have these three different integrals to compute, and I want to make sure that you're clear on the different roles that the different variables play. So let's see here. For the inside integral. Oh, whoops. Oh, yeah, I'm at the... Okay. For the inside integral, x is the variable. Right, so all the antiderivatives are going to be with respect to x. You're going to treat y and z as constants because they are constants, right? You look back at our slicing process. In the slicing process, we only got to the x integral after having chosen fixed values of y and z. Said differently, when we get to the inside integral, the outside differential variables are to be treated like constants because they are constants. Right, so it's a nice way to remember it. Any variables that are further to the outside in the integral, for the purposes of that integral, you treat them as constants. So for the x integral, in this case, the order that I'm doing dx, dy, dz. For the inside x integral, y and z are to be treated as constants. Okay, and likewise as you go further out, if you look at, let's look at this, I missed, try that again. Look at this second integral. In that second integral, y is the variable. And the variable, there's only one variable further to the outside, that's z. We treat z as a constant. And remember, as we went through this slicing process, when we got to doing the y integral and thinking about the range of values of y, we got to it having already chosen to fix a certain value of z. So we treat z as a constant because it is a constant. Yeah, everybody happy? By the way, notice that there's no x's left. In this inside integral, y is a variable, z is a constant, and x is gone. It integrated out already. Okay. All right. Okay, and then of course for the outside integral, there is only one variable left. It's z. It's a single variable. Why did I do that in gray? It's a single variable integral, and so it is, the variable. Okay. So all I have left is a bunch of examples, and I'm hoping we can get at least partway through this next example in the next couple minutes here. But there's several examples I want to show you. It's just, triple integrals, there's all sorts of different kinds of scenarios that can come up, and I think it's worth seeing all of them. So we're not going to finish this section today. But anyway, here we go. We're going to start with the unit ball. And suppose we want to compute a triple integral. Now, again, like I promised previously, I want to talk about where this triple integral comes from. I don't know. Maybe I'm computing a mass, and F represents mass per unit volume. Or maybe I'm counting bugs, and the integrand represents population density of bugs. Right? Or maybe I'm computing the total quantity of pollution in a certain part of the atmosphere three-dimensionally, right? And I know concentration is, per unit, quantity per unit volume of pollution or whatever. So let's not worry about the application, what that application is. All that application is it's just going to tell you what F is, what kind of a density. So that being whatever it is, what I want to talk about is how do I turn this triple integral into this nested integral for the, given the shape of this particular domain, this unit ball. Okay. Now again, pretty arbitrarily, I'm slicing in an arbitrary order here. I'm doing the X slicing first. It doesn't matter. In this case, it's ball, highly symmetric. Okay, but let's go through the process. What about X? What's the range of values of X? We got to look at our picture here. By the way, I cheated when I drew this picture. I did this on because it's kind of hard, right, to take a ball and draw slices of a ball and make it look sort of realistic. So anyway, I got a computer to do this, and I printed it and traced it. So anyway, you're welcome to do that kind of thing just for the practice. But I would encourage, thinking through, if you have something to trace, and as you're tracing, you can sort of make sense of, okay, what are the choices that are being made here, artistically, and how does this make it look the way I want it to look? Okay. So here's where our slicing process looks like in the X direction, right? As you're going in the X direction, slices are going to be kind of like that, right? And the first slice is going to happen way back at the back of the sphere. This is a unit sphere, so that's clearly going to have x negative 1. The last slice is going to happen at the very sort of front, if you will, of the sphere. Again, unit sphere, so this is going to be where x is equal to plus 1. All right, so I'm just going to let that be. Okay, now, as per our process, having written down these bounds, x goes from negative 1 to 1. The next question we want to ask is we're gonna fix an x slice. We're gonna fix a value of x. Look at just that one x slice, and now I want to know the range of values of z arbitrarily. So again, here's my picture. We're gonna fix this value of x. So we're gonna focus now entirely on this x slice. On that x slice, that value of x being fixed, I want to know the range of values of z. So now, again, I appeal to your geometric intuition. A z slice, right? Here's our x slice. Our x slice is vertical. Our z slice is horizontal, and you have to use your imagination. What happens when a slice of this shape gets cut through and sliced by a slice of this orientation, right? And it makes a little line segment again, like that. By the way, that's always going to happen, right? Slices of slices are always line segments. Right? So these are what our z slices look like, and I need to know where do they start, where do they end? Well, the last one's going to be this z slice down at the bottom of this x slice, which is going to have some z coordinate that we got to figure out how to deal with, right? And then the last slice is going to give us our upper bound. It's going to be this point up at the very top of our x slice. So this is the geometry of our situation. Is everybody on board? Try to visualize this three-dimensionally. By the way, this is another situation where I think it's worth it to buy a sack of oranges and slice it up. Right? You can have an actual three-dimensional model of what you're trying to make sense out of. I definitely encourage that. Okay. All right? Or maybe Play-Doh or something so you can use it over again, less messy. Okay, so I'll give you a quick preview of what we're going to talk about next time, and that is that, well, in order to find these bounds, we're going to have to figure out what can I say about these points, what do I know about those points, and we're going to write it down algebraically and then solve for what we're interested in, namely we're going to solve for Z. We'll pick up here next time. See y'all later. Oh, quick announcement.